Tiebreakers are devices utilized in electrical distribution systems to prevent parallel connected sources such as generators or transformers from operating out of sync. Their primary function is to ensure that these sources maintain synchronization and deliver power to the grid in a stable manner. Tiebreakers are normally closed switches that continuously monitor the phase difference between the two sources they connect. When this phase difference exceeds a predetermined threshold, the tiebreaker opens, disconnecting the sources. This action prevents out-of-sync operation, which can potentially cause damage to equipment and lead to instability in the electrical grid. In large facilities, including power plants and substations, tiebreakers are essential for ensuring stable and reliable operation of the electrical system. Their operation typically involves 4 key stages: firstly, monitoring; secondly, synchronizing; thirdly, tripping; and fourthly, reclosing. During the monitoring stage, tiebreakers continuously monitor the phase difference between the sources they connect. In the synchronizing stage, when the phase difference is within the allowable range, the tiebreakers remain closed. This allows the sources to operate synchronously and supply power to the grid. If the phase difference exceeds the threshold during the tripping stage, the tiebreakers open, disconnecting the sources and preventing out-of-sync operation. Following a predetermined time in the reclosing stage, the tiebreakers attempt to reclose to reconnect the sources. If the phase difference is still within the allowable range, the tiebreakers will remain closed. However, if the phase difference still exceeds the threshold, they will trip again. There are several types of tiebreakers available, including firstly, manual tiebreakers; secondly, automatic tiebreakers; thirdly, phase difference protection tiebreakers; and fourthly, slip frequency protection tiebreakers. Manual tiebreakers are operated manually by personnel. Automatic tiebreakers are controlled by protective relays that monitor phase differences. Phase difference protection tiebreakers trip based on a direct measurement of the phase difference between sources. Slip frequency protection tiebreakers trip based on the frequency difference between sources. Tiebreakers play a critical role in maintaining system stability and preventing blackouts. They ensure that parallel connected sources operate synchronously, deliver power reliably, and protect the electrical grid from damage due to out-of-sync conditions. Understanding the function and operation of tiebreakers is crucial for engineers and technicians involved in the design, operation, and maintenance of electrical power systems, particularly in large facilities where the consequences of system instability can be significant. The threshold for phase difference that triggers the opening of a tiebreaker is a critical parameter that needs to be carefully determined based on the specific characteristics of the electrical system and the connected sources. This threshold is typically set to a value that is high enough to allow for normal variations in phase difference, but low enough to prevent damage to equipment or instability in the grid. The predetermined time delay before a tiebreaker attempts to reclose is another important parameter. This time delay needs to be long enough to allow the phase difference to return to within the allowable range, but short enough to minimize the duration of any interruption in power supply. Protective relays play a vital role in the operation of automatic tiebreakers. These relays are designed to monitor various parameters, including phase difference, frequency difference, voltage, and current, and to initiate a trip signal when these parameters exceed predetermined limits. The design and selection of protective relays for tiebreaker applications require careful consideration of the specific characteristics of the electrical system and the potential fault conditions that may occur. The maintenance of tiebreakers is also essential for ensuring their reliable operation. Regular inspections, testing, and maintenance procedures should be performed to identify and address any potential problems, such as worn contacts, loose connections, or faulty relays. The complexity of tiebreaker systems can vary depending on the size and configuration of the electrical system. In some cases, tiebreakers may be integrated with other protective devices, such as circuit breakers and fuses, to provide a comprehensive protection scheme. The coordination of these protective devices is crucial for ensuring that faults are cleared quickly and effectively, minimizing the impact on the rest of the system. The use of digital relays and communication networks has enabled the development of more sophisticated tiebreaker systems with advanced features, such as remote monitoring, control, and diagnostics. These features can improve the reliability and efficiency of the electrical system and facilitate faster response to fault conditions. The application of tiebreakers is not limited to power plants and substations. They can also be used in industrial facilities, commercial buildings, and other large electrical systems where multiple sources of power are interconnected. In these applications, tiebreakers can help to improve the reliability and resilience of the power supply, ensuring that critical loads are not interrupted in the event of a fault or outage. The selection of the appropriate type and size of tiebreaker for a particular application depends on several factors, including the voltage and current ratings of the system, the fault current levels, the type of sources being interconnected, and the desired level of protection. Consulting with experienced electrical engineers and equipment manufacturers is essential for ensuring that the tiebreaker system is properly designed and installed. The cost of tiebreakers can vary depending on their type, size, and features. However, the cost of not having tiebreakers in place can be much higher, especially in large facilities where the consequences of a blackout can be severe. Investing in a reliable tiebreaker system is therefore a wise decision for any organization that relies on a continuous and stable supply of electrical power. The integration of renewable energy sources such as solar and wind power into the electrical grid has increased the importance of tiebreakers. These renewable sources are often intermittent and can cause fluctuations in voltage and frequency, which can lead to instability in the grid. Tiebreakers can help to mitigate these effects by disconnecting renewable sources when they are not operating synchronously with the grid. The development of smart grid technologies is also driving innovation in tiebreaker systems. Smart grids utilize advanced sensors, communication networks, and control algorithms to improve the efficiency, reliability, and security of the electrical grid. Tiebreakers can be integrated with smart grid systems to provide real-time monitoring and control of power flows, enabling faster and more effective response to fault conditions. The future of tiebreaker technology is likely to involve further integration with smart grid systems, as well as the development of more advanced protective relays and communication networks. These advancements will help to ensure that the electrical grid remains stable and reliable, even as it becomes more complex and integrated with renewable energy sources. In addition to their technical aspects, tiebreakers also have important economic and regulatory implications. The cost of blackouts can be significant both in terms of direct financial losses and indirect economic impacts. Regulators often require utilities and other large power consumers to implement measures to prevent blackouts, including the installation of tiebreakers. The design, operation, and maintenance of tiebreaker systems are subject to various industry standards and best practices. These standards provide guidance on the selection, installation, testing, and maintenance of tiebreakers, ensuring that they are operated safely and reliably. The training and certification of personnel who work with tiebreaker systems are also important for ensuring their safe and reliable operation. Proper training can help to prevent human errors that could lead to equipment damage or system instability. The use of simulation and modeling tools can be helpful in designing and testing tiebreaker systems. These tools can simulate various fault conditions and assess the performance of the tiebreakers under different scenarios. The results of these simulations can be used to optimize the design and settings of the tiebreakers, ensuring that they provide adequate protection for the electrical system. The ongoing monitoring and analysis of tiebreaker performance are also important for identifying any potential problems and preventing future failures. Data from protective relays and other monitoring devices can be used to track the performance of the tiebreakers and identify any trends or anomalies that may indicate a problem. The sharing of information and best practices among utilities and other power system operators can help to improve the reliability and security of the electrical grid. Collaborative efforts can lead to the development of more effective tiebreaker systems and improved responses to fault conditions. Tiebreakers are an essential component of modern electrical power systems, playing a critical role in maintaining system stability and preventing blackouts. Their proper design, operation, and maintenance are essential for ensuring a reliable and secure supply of electrical power. As the electrical grid becomes more complex and integrated with renewable energy sources, the importance of tie breakers will only continue to grow. The function of tie breakers, as explained, is critical in preventing damage and instability in electrical systems, particularly in large facilities. Tie breakers achieve this by monitoring the phase difference between power sources, tripping when the difference exceeds a safe threshold, and reclosing only when synchronization is restored. This process ensures a stable and reliable power supply, safeguarding equipment and preventing costly blackouts.